Hey, period 3. Bell rang with about 5 minutes of lesson left to go, so I'm just going to quickly do this because I can. We spent all this time developing the formal definition of a limit and giving the formal definition and doing a proof, but what we didn't get to was the easy part, which is just doing a bunch of limits. So let's talk about that for a minute. So I'm going to do 4 problems. This should take 5 minutes. 5 problems I'm going to do. So let's take the limit as n approaches infinity of n plus 1 over 2n. Well, based on your knowledge of rational functions, you kind of probably already know what happens to this expression as n goes to infinity. It's going to look more and more like 1/2. And I suspect that most of you would be able to just guess that the answer is 1/2, and that is in fact the correct answer. But it's good habit and good practice to show a little bit of work about this, and there's a typical thing that we do when we're interested in the limit as n goes to infinity. We multiply the top and bottom by the highest power of n in the denominator. In this case, in the denominator there's an n, so I'm going to multiply by 1 over n over 1 over n. This is really nice because it allows me to write my expression in a more simplified form. When you multiply that through, I get 1 plus 1 over n over just 2. This is really good because it's very, very obvious that as n goes to infinity, 1 over n goes to 0, and therefore this is going to look more and more like 1/2, and so the answer is 1/2. Hopefully that makes total sense. Good. Okay, doing a couple more really quick. Number 2, let's do the limit as n goes to infinity of 5n squared minus 16 over 3n cubed plus 4n plus 1. Now here, again, it's pretty obvious, especially people who are experienced graphing rational functions, that since this numerator is a quadratic and the denominator is a cubic, then I think this limit is going to be 0, and that is the correct answer. Still though, I think it's good practice to write a little bit more here, and so what we do is, again, divide by the highest power of n in the denominator, which is n cubed. So I'm going to multiply by 1 over n cubed over 1 over n cubed, and when I do so, it enables me to simplify this expression a little bit more. Multiplying that through the top, you get 5 over n minus 16 over n cubed, all over 3 plus 4 over n squared plus 1 over n cubed. This is nice because this obviously goes to 0, this obviously goes to 0, this obviously goes to 0, and this obviously goes to 0 as n goes to infinity. So this is looking a lot like 0 over 3, and thus the limit is 0. And you've showed some work and you've demonstrated why this is so. Okay, 3 more. Take the limit as n goes to infinity of 3n to the 4th minus 6n squared plus 1 all over 5n cubed minus 8. Well, here I think it's pretty obvious that since the numerator is a quartic and the denominator is a cubic, then the numerator is going to grow much, much faster than the cubic, and this thing is just going to blow up. And indeed, if I multiply, again, following the same rule, divide the top and bottom by the highest power of n in the denominator, if I do that, then I'm left with, this becomes the limit, as n goes to infinity, of 3n minus 6 over n plus 1 over n cubed, all over 5 minus 8 over n cubed. And now again, this goes to 0, this goes to 0, and this goes to 0 as n goes to infinity. So this is looking a lot more like 3n over 5. And what happens as n approaches infinity to 3n over 5, this goes to infinity. Now, infinity is not a number, and in fact, if you look back at our definition of what it means for a function to have a limit, what we actually say is this sequence has no limit. Has no limit. It has no limit because there is no one number which the terms of this sequence are getting closer and closer to as x goes to infinity. In fact, what happens to the terms of this sequence, the terms of the sequence just keep getting bigger and bigger and bigger. Since the terms of the sequence just keep getting bigger and bigger, there is no limit. Full stop. This sequence has no limit. Even though this sequence has no limit, we still write infinity over here. And when we write infinity, that doesn't mean that the sequence has a limit. It just means that it doesn't have a limit. And infinity is describing the way in which it does not have a limit, or the reason which it does not have a limit. It does not have a limit because the terms go to infinity, which means they just keep getting bigger and bigger. So that's an important distinction. Okay, one more, two more, a little bit more complicated ones. The limit as n goes to infinity of maybe something like this, right? The arc cosine of n plus 1 over 2n. I could ask you something like that. Well, now what happens as n goes to infinity, this is sort of an example like number 1. What did we learn about number 1? We learned that the inside of the arc cosine is getting closer and closer to 1/2. So this limit is just arc cosine 1/2, and arc cosine 1/2 is pi over 3. So the terms of this sequence are getting closer and closer to pi over 3. Okay, last one. What if I tell you this is the limit as n goes to infinity of -1 to the n, or something like that? Well, this is a very weird one. I'm not sure what this is. So let's just take a look at this sequence. What kind of a sequence is this? Well, when n is 1, this sequence is -1. When n is 2, the sequence is 1. When n is 3, the sequence is just -1 again. So this is just a sequence which just alternates back and forth between -1 and 1. We can make a graph of this. Looks like this. 1, 2, 3, 4, 5, etc. When I plug in 1, I get -1. When I plug in 2, I get 1. When I plug in 3, I get -1, etc., etc. So what do we say about this sequence? Is there some particular number which the terms of this sequence are getting closer and closer to? Nope, there isn't. And this just limit, the answer to this is just no limit, or the limit does not exist. Okay, that should be enough for you to be able to complete your homework. On the packet that I handed out, you can read it. It's all the stuff that we did today, and there are a whole bunch of problems that you have to do that are kind of like this. And so now you know what's expected, and we'll go over them next class. Okay, sorry about this, and please watch the video. Bye. See you next class.